All right, good morning, Space for America Cup, day 2. We are at our session for JPL Mission to Mars, focus on perseverance. We've got Jeff McGivern here today, who is a mechanical systems engineer for the Perseverance mission. My name is Holly Gummel. I will be the moderator for this session. We'll leave about 10 minutes at the end of the talk today for Q&A. Please post your questions at the Q&A channel on the right of your screen, and we'll address those at the end of the session. Thank you so much, Jeff.
Cool. Thanks, Holly. Well, hi everybody. I have a lot to cover. I'll try not to go through things too fast, but the intent will be if you have questions about any specific topic, ask them at the end, and I'll cover them at that point. All right, so I'm going to share my screen for some pictures to talk to. Like Holly mentioned, I'm currently at JPL, and I was a mechanical systems engineer for Mars Perseverance rover. Specifically, I worked on the sample caching system. And today I'm going to talk a little bit about Mars 2020 and the Perseverance mission up against some historical missions, and talk a little bit about some of the details of what we've achieved so far, what we have coming up soon. I'd be remiss if I didn't wish everyone a happy Juneteenth. Of course, today being June 19th. The image on the left was captured by NASA in celebration of Juneteenth. That's Galveston, Texas. And of course, June, happy Pride Month to our LGBTQ plus community. We have a strong one at JPL, and the image on the right is from our Spectrum group, which is our LGBT plus group. So on to Mars. So this is about 500 of my Mars 2020 colleagues. The team's bigger than this. This was, as you can imagine, this was taken pre-COVID, July 19th. What I really enjoy about the space program, what I really enjoyed about our team is how many folks were involved and how just diverse across so many different categories we were. And if you were trying to find me, I'm right there, standing in the crowd. So Mars 2020. Mars 2020 is the latest in a string of Mars missions. In the late 60s, NASA sent a variety of Mariner-class spacecraft. Mariner explored a few planets in the solar system, like Mercury, Venus, and Mars. And I'll be laying the Martian flavor up against Viking. Viking was a pair of spacecraft, Viking 1 and 2. Both went to Mars. The orbiters were JPL spacecraft, and the landers that were attached were Martin Marietta. And so Viking was in the late 70s. And then, of course, Mars 2020, our most recent rover expedition to Mars, that's cruising on the planet right now. So what's Mars 2020 doing? Our major science objectives are what you see here. So geology is a big piece of it. We're trying to understand rock formations, what Mars is made of, what the terrain looks like, any analogs we have back to Earth. We have a few pieces of instrumentation on the rover to help us do that. Astrobiology is a major objective of this particular mission. We are looking for signs of life. The area that we landed, Jezero Crater, one main reason it was chosen is because it has terrain formations that look like a dry lake bed, and I'll show you some pictures of that in a minute. And on Earth, we know of very few better places to host life than where water is churning up soil, where a river dumps into a lake. And so that's astrobiology. Mars 2020 is the first phase of a sample return mission. So in order to return samples, we need to collect them. And so objective C is sample caching. We have hardware on the rover, a drill at the end of a robotic arm, and a bunch of sample handling mechanisms underneath the rover to enable that sample caching. And then objective D, preparation for humans. We have a variety of instrumentation and experiments on the rover to help us understand if we can go and explore there safely, and if we can, what we need to be prepared to do. So I'll talk a little bit about one of the main pieces of experimentation that we've been using called MOXIE, the Mars Oxygen In Situ Experimentation Unit. So essentially it's the a little box that turns carbon dioxide into oxygen. So those are the four driving objectives of Mars 2020. So on the left, you have one of the Mariner spacecraft in 1967 in one of our clean rooms at JPL. And on the right, you have Mars 2020. Mars 2020 is upside down if you think about how it entered Martian atmosphere. So the rover would be upside down, wheels up, and this is the heat shield. So you can see some key differences. No masks in the clean room in 67, fewer gloves, and different flavor of clean room protocols. One other major difference between these two missions, other than just when they happened, is the Mariner missions were flyby and orbiter missions, so nothing landed. And of course, Mars 2020 is exclusively a landed mission. So I just think it's neat to look at this kind of historical perspective of work in the clean room on an early mission and work in the clean. And this is, so I guess it's worth highlighting. This is before COVID, right? So this image was taken in 2019 as we were preparing to shake the system. We do a dynamics test, we shake it. And for our clean room activities, we didn't have to adjust too much for COVID. We were already wearing masks, we're already wearing gloves in our clean room protocols as part of our contamination control and planetary protection activities. So JPL mission control, these two images are the same room. This is the Space Flight Operations Facility at JPL. This is our Mission Control Center, building 230. On the left, this is 1968, actually in support of some of the Mariner activities. And on the right is launch day for Mars 2020. Some of the computer systems are more up to date. Some of the screens are fancier and the chairs are a little more ergonomic. Otherwise, we use the mission control nearly identically to how we used it before. We receive telemetry, we receive information about the mission, we use it as a place to coordinate and strategize about what we're doing on a particular mission. And we all like to stare up at the big TVs. So having a propulsion background, I always enjoy looking at the rockets. So the Mariner launch and the Mars 2020 launch are both on Atlas class launch vehicles. Of course, the Mariner is much closer to its ICBM heritage than the Mars 2020 launch. All three of these are out at Cape Canaveral. Something I'll note, and if you look at the link in my biography on the America Cup page, you'll see I grew up in Florida. So I grew up on the Space Coast with launches. So this flavor of the space program is nostalgic for me, watching launch vehicles launch into space. And so you have an early Atlas, you have a Titan launch vehicle for Viking, you have Mars 2020 on the right. So Mars 2020, of course, was launched on an Atlas V. Atlas V used a couple of solid rocket boosters along with RD-180 Russian first stage engines and RL-10 upper stage, which is liquid oxygen, liquid hydrogen. Here's a pad camera shot of the launch. You can see drops from the water, probably a mixture of exhaust and the flame bucket water. These are lightning rods that are around the launch pad. And then I really enjoy shots like this because to me, this is home. So this is the Atlantic Ocean on the right, Cape Canaveral on the left, and of course the Atlas V launching Mars 2020 into orbit. So if you're following along, I started with spacecraft assembly and checkout. Now we're into launch, and launch is just the start. you haven't even started doing any mission objectives. At JPL, we haven't started achieving any science objectives. And it takes about 7 months from launch on Earth to arrival at Mars. We call this the cruise stage. So 7 months of cruise to get to Mars, and this we have this opportunity every 26 months. So every 26 months, because this image doesn't show it, but the orbits are elliptical around the sun, and because of the shape of those orbits, we are closest to Mars in this kind of orientation to have a reasonable amount of propulsion energy needed to get there in 7 months. So if we miss our launch window, we have to wait 2 years, and this actually happened with Curiosity. Curiosity was delayed 2 years because of some early development. Curiosity, of course, is the Mars Science Laboratory, and that 2 year wait time was because we were waiting for the orbits of the planets to realign. And after you cruise for 7 months, you get a little tired of looking at this. But then a planet shows up. You think it's Mars. You're not sure. Get a little closer. That's Mars. That's absolutely Mars. Around this time, we're deep into entry, descent, and landing expectations. You can't make course corrections anymore. Where you're headed is where you're going to head, especially when you're careening towards a planet. We make trajectory corrections along the way. But once you show up at Mars, this is around the time, this is landing day. everyone's in the control center. We're ready for the 7 minutes of terror if you followed any Martian missions. And this is the beginning of our Martian mission. I think this, so I love this picture of Mars on the right, by the way. That's actually 102 images stitched together from Viking 1 and Viking 2. So the picture of Mars on the right is from the 1970s. The picture of Mars on the left is from Mariner 4. So this was a flyby mission, and it's just one picture of Mars as it was flying by. And the picture on the left is the earliest close-up shot that humanity ever had of Mars. And so when we received this picture back, you can imagine we were bit by the bug of visiting this place. So these are all of the Martian landing sites that JPL has gone to, and actually it's all of the major missions of society except for Tianwen-1. So what's so interesting about this time period of Martian exploration is we're not alone. So last year, we launched our mission, but before that, the United Arab Emirates launched their Al-Amal Hope orbiter, and the Chinese space program launched their Tianwen-1 rover that's just starting to cruise across the surface. And so you can see we've covered a variety areas. Phoenix is considered a polar science mission because it's so close to the poles. Of course, this is Mars stretched out into a rectangle. And here's Perseverance landing in that Jezero crater. Here's Viking 2 and Viking 1. Some of the potential landing sites for Perseverance were closer to one of our previous missions to collect data on similar conditions, but we opted for this dry lake bed crater for the potential of astrobiology science objectives. And specifically, here's where we landed. I'll go back to that overview shot. So here you can see Perseverance the edge of Jezero Crater, and here's the edge of Jezero Crater. This is the crater rim. So you can see you have this river. I'm using this loosely. There's no running river there right now. But if I were to color this blue and green, you'd say that's on Earth. So you can see this river-looking terrain structure dumping into this lake-looking terrain structure, and in this delta, this where a river meets a large body of water is, like I said, on Earth where we usually see a lot of signs of life. And so this is the landing target that we use for planning. It's about a 4 mile, 4.5 mile circle, but of course it's not a circle because of the direction we're coming into the orbit. We like to be as precise as possible. This mission was particularly advanced in the way we tackled landing. And we used a lot of AI, machine learning, and onboard decision making. Because a signal takes about 7 minutes, between 7 and 14 minutes, depending on where you are, to get from here to Earth and back. And landing takes about 7 minutes. So by the time we've landed on the surface, I said that backwards. By the time we've received the signal to tell us that we've landed on the surface, we have already not landed or landed. And so we call that 7 minutes of terror because it's thousands of us holding our breath at the same time and only breathing again after 7 minutes.
Propulsion, go. EDL phase leap, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So what just happened? That's a very compressed timeline. So that was about 1 minute, which is actually 7 minutes. So we entered the atmosphere. We use aerobraking, so we use the atmosphere to slow us down. But because the atmosphere of Mars is only 1% that of Earth, it takes, we end up a lot faster at the end of it than we would be on Earth. And it takes a lot larger surface area in order to achieve that. So by the time we deploy the parachute, we're still traveling supersonically. So we're deploying these parachutes in supersonic conditions that we don't nominally have here on Earth. And we use rocket sleds in order to test those out. So once you deploy your parachute, you drop off your heat shield, that exposes the descent stage. After you expose the descent stage, you get your first look at the surface. And the vehicle's making its automated decisions on where it's going to land. That's what this terrain relative navigation is. You find a solution, and then you proceed to go there. So this is the descent vehicle breaking away from the back shell, leaving the parachute behind, and we have powered descent. So we're navigating to the chosen landing site, and then you lower the rover to the surface, you cut the rope, and the descent stage crashes in the distance. By the way, it's just not, and when I say cut the rope, it's literally rope. We're lowering, oh, sorry, there we go. Lowering the rover to the ground using nylon rope. So here's that process in pictures. So you pop your chute, that's the chute being deployed off the top of the spacecraft. It starts to open up, and then you have a fully filled chute. So at this point, you're just starting to slow down. You're still traveling supersonic speeds. So after you slow down enough, you drop the heat shield. This is a rover down look camera, and the heat shield's falling away from the rover. After the heat shield's out of the way, you can see the ground. This is one of the first images we took of the Martian surface from the terrain relative navigation cameras that's helping us find where we're going to land. So we take this picture, and the system starts to evaluate what's a rough zone, what's a good zone, what's a bad zone, based on some criteria that we programmed into it. So after taking a bunch of those pictures, making its landing solution, we start to lower the rover. So this is a descent stage down look camera. That's the top of the rover. And we lower the rover away, and on the right, there's an up look camera from the rover looking at the bottom of this descent stage. So this is this point where the descent stage is powered, and it's lowering over to the ground. And then just above the surface, so you can see like images like this, because you can see a bunch of the interactions. So you can see where the propulsion system is scarfing the ground and kicking up dust. This image is cloudy because of all the dust we're kicking up, because we're so close to the ground and lowering the rover onto the ground. And then there's some sensors in the ropes. These are the nylon ropes. There's some load sensors up at the descent stage. And once we sense that the ropes are starting to go slack, we cut the system, and the descent stage flies away. So that's landing. What's cool about this landing is we could see it with other spacecraft. So this is a shot from the HiRISE spacecraft, and there's the parachute. There's the descent stage coming in for landing. And after we landed, we could see it with the Mars reconnaissance orbiter. So this is a shot from the Mars reconnaissance orbiter. Again, so there's the rover, and you can see the where the propulsion system impacted the ground, where the flames were blowing up dust on the ground. So after we land, we start to bring up our rover systems. And one of the early shots we have is from one of our hazardous cameras. We call them HazCams. They're hazardous navigation cameras. They help us when we're driving, understanding where obstacles are, where rocks are. This is a shot of where the descent stage flew off and crashed into the ground. So this is a plume of smoke from the crashed descent stage in the distance.
We are starting to straighten up.
Oh yeah, so what I have here is what I just walked and what it sounded like and looked like the day of.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter confirmed. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here in safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So I can't watch that video enough. So Tango Delta, that's touchdown. That's confirmation that we have landed and we've received the signal from the rover after landing. So the voice you heard through most of that is Dr. Swati Mohan. She was leading the landing activities for landing day. And you can hear her talk about the different stages of EDL. And remember what I said, it takes 7 minutes for that signal to come back to Earth. So by the time she's reporting on it, it happened 7 minutes ago. And so after you land on the surface of Mars, and it's been a rough ride, right? If you've ever been on a road trip, you know, riding in a car for a few days can get pretty tiring. Flying through space for 7 months, you can imagine it can be pretty tiring. And imagine that for a set of astronauts going to Mars. So after 7 months and a rough landing and dust kicked, you rub your eyes and you take your first look. This is the first image from Mars 2020 on the surface of Mars. The lens cover is actually still on, so this rim is the lens cap to protect from all of the dust thrown up during the landing event. This is one of the first real pieces of evidence that we use to know that we landed safely, or at least mostly safety. We haven't started the system checkouts yet. So after we get the rest of the systems up, start doing, we call them wiggle checks. We wiggle the actuators to make sure everything's alive, wiggle checks and aliveness checks. We take a look around. So this is one portion of a big panorama looking around our immediate environment. So the hill you see growing in the distance to the right is the rim of the crater. We're going to be driving towards that rim here shortly. And this gives us our first look at what potential science targets we have in our immediate environment. And we like to understand where we think we landed and how good a job we did. If you've been, if you followed other Martian missions, you know, we like to take a picture of our feet. So the picture on the left is of the Viking footpad landed on Mars. So the picture on the left is one of our first pictures from Mars of a landed spacecraft. And of course, the picture on the right is from Perseverance of our wheel landed on Mars. So there's a picture from the 70s on the left. That's Viking in its, I don't remember which Viking spacecraft it is, but that's one of the Viking spacecraft in its landed location, just starting to do some of its science. And the GIF on the right is Perseverance looking at the Ingenuity helicopter. So one other aspect of how the landing sequence chose its final landing location is to look for a smooth enough location to drop off that Ingenuity helicopter in order to fly on Mars. These are comparisons of two panorama shots. If nothing else, we've really figured out how to take a sweet panorama shot of where we've landed on Mars, you know, or in case of the rover, where we've driven. So of course, again, the top is Viking and the bottom is Perseverance. And again, this isn't the full panorama. You can go to the NASA Mars website for all sorts of images like this. I think it just gives us a really neat perspective of what we've been able to do in the past and what we can do now. And you can see, so the camera for Perseverance is in the mast. It's the head of the rover, and the camera for Viking is just on the top deck. So we call the top of the landed spacecraft the top deck. So we have a lot more capability with a camera on a swiveling head than you might on it with a camera on a top deck. So here's a few of the activities we've been doing so far on the surface. The top left there is the Ingenuity helicopter. This is a video taken from a camera on the rover. So there's the Ingenuity helicopter taking off. It's going to fly to the right. We've been flying different flight patterns. We log all our time per FAA regulations. So we have a log book here on Earth, and we track all of our powered flight activities. In a second, the Ingenuity helicopter will fly back onto the screen. Ingenuity is a tech demo. It's not even part of the primary mission, but it's been such a huge success and has strong implications for what we'll be able to do on the surface of Mars in the future. The only thing on it is a little solar power generator and a couple of cameras, and that's it. And then some communications to talk back to the rover. It can't talk directly to Earth. It sends all of its communications through the rover. So that's Moxie there in the top right, gold-plated, incredible piece of experimental instrumentation, turning carbon dioxide into oxygen in support of what we might do in the future with humans, and wildly successful. What's interesting about Moxie is we can't do anything else with the rover while we're using Moxie. Moxie takes so much power that there's none left to do anything else on the rover. So it's a difficult process to implement, especially implement remotely. Sherlock and Watson are two pieces of instrumentation on the end of the robotic arm. The image there on the bottom left is a zooming in GIF from Watson. So we use Watson to take macro shots to understand potential targets, and then Sherlock takes slightly more micro shots to understand the composition of that rock. And we've also been doing checkouts of the sample caching system. So like Holly mentioned, I supported the sample caching system activities. I was leading the SCS sample caching system, the SCS environmental test campaign called QMDT, qualification model dirty testing. We had all of this arm and core and sample handling hardware in a big thermal vacuum chamber at JPL with rocks in the chamber, and we were collecting samples and doing all the things that we're about to do on Earth, on Mars, here on Earth, to make sure that we understand how the system works and understand how to run those operations. So what do we have coming up? First, I'll talk a little bit about SuperCam. SuperCam is a camera that's up in the mast. What I find so intriguing about SuperCam is it's more than a camera. So the camera itself is a phenomenal piece of optics, but it also has paired with it a LIBS system, laser induced breakdown system. So as part of SuperCam, we're blasting rocks with a laser to pop them, and we listen to that sound, and that sound plus the images we capture tell us what the rock is made of. Awesome. So the image on the left there, that's our plan coming up. So right now we're still in the landing area. Something you might have noticed and might have been paying attention to, we've been naming all of the areas and rock formations and terrain formations that we find in this area for Mars 2020 using words from the Navajo language. And one of my team members, Aaron Yazzie, who is a member of the Navajo Nation, he's been supporting naming those things with proper Navajo Nation terms. And so the Sita and Maz, the Maz rock that we saw are all Navajo names. So what we're about to do is we're about to drive, and the white circles are potential interesting science targets. So we're going to drive to these white circles and do some sample collection, do some inspections, use our instrumentation to understand what the different rocks are made of, and if they're interesting enough to our geologists and astrobiologists here on Earth, we will collect samples. We can only collect 42 samples, and we can only bring 30 of them back as part of the Mars sample return mission. I don't have much about the Mars sample return mission, but if you have any questions, I've worked that a little bit and can talk about that more in the Q&A section. So we're about to embark on our science journey. We're done flying the helicopter. We're ready to go and collect some samples. This is an animation of the sample caching system. So the arm on the front of the rover has the core on it. We do this to show the core. These are the two stabilizers that you see on the top and bottom of the core, and we lower it and load up against the ground and then extend the drill bit into the ground to collect the core. So this is on stowing. We on-stow the robotic arm and go and get the core. This presumes that you already have the right drill bit loaded into the core, the drill. Then it's a percussive drill, so it's percussing and rotating to drill and form a core out of the rock. And then we break that core off, and there's a sample tube inside of the drill bit. And then we go and drop that drill bit back off and pull that. What's highlighted yellow there is the sample tube inside the drill bit. Then we have another little robotic arm underneath the rover called the sample handling arm. We pull the sample tube out of the drill bit. We do some initial inspections of the sample. So this is the volume station. We measure how much volume is there. We take some pictures of the top of the sample and the top of the sample tube as a means to catalog what we can know about the sample. At this point, we can't interact with the sample other than taking pictures of it. Then after we take those pictures, we seal the tube. So what it did just before that station was insert a metallic seal and deform it into the tube. So now that sample is hermetically sealed inside the rover. And for the Mars sample return mission, we'll be dropping off those samples onto the surface for the Mars sample return fetch rover to pick up and insert into the ascent vehicle. So there's Mars 2020 driving off to do some more exploring. we're nothing without our team. So the image in the bottom and the middle is the one I showed at the top of the presentation, and all the other images around the this chart are from different parts of Mars 2020 and JPL. This is in France, right? This is in mission control. This is in one of our clean rooms. This is how we've been set up for operations during COVID time. So we have a specific station. This in particular is the helicopter team supporting helicopter operations. We are one of the most rewarding aspects of working in the space program and working at JPL is the diversity and wide range of people that I get to work with, and the passion that they all have for space exploration is inspiring. There are very few industries that you get collaborations between the United Arab Emirates and the Japanese space program. Of course, the global space program is one of those industries because the United Arab Emirates launched their Al-Amal Mars probe on the Japanese launch vehicle. And so this is the latter half of that landing event, starting with Tango Delta, and that's Swati Mohan.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
And that's my talk. I went a little over, but happy to take questions. I think Holly is going to moderate that for me.
That was awesome. I like the cat on Mars there. All right. Yes, we do have a couple of questions. We've only got about 5 minutes left. If we can get through what we've got. Can you hear me okay?
Yeah, I'm good.
Great. So I've got one question on the Perseverance. Is there any translucent material, any windows, anything like that? And if so, what material do you use?
There's all kinds of materials on the rover. I guess I don't know what they mean by translucent necessarily, but there's different like glass and things like that. I mean, there's different ceramics. We certainly have transparent elements because we have lens covers, and like you saw, you could see through the lens cover. But we have lots of aluminums and titaniums and paints and coatings and nickel-based alloys. Lots and lots of different materials.
Sorry, are the lenses glass?
Say again?
Are the lenses just glass? What?
No, I don't think so.
Okay. With the sample cache system, is the recovery mission designed yet? What are going to be the main challenges with interfacing with the cached samples?
You know, picking up the actual samples will probably be some of the easiest part of the mission. And I only say that because the samples themselves are relatively simple. The sample tubes, they're cylinders. They have some points that you can interface with them. Some of the more difficult aspects of Mars sample return will be all of the interfaces on the mission. So it's a really big mission, and there are JPL elements, Goddard elements, Marshall Space Flight Center elements. The European Space Agency has major elements as part of the Mars sample return mission. So integrating all those systems and getting all those systems to work together once we get to Mars that's going to be difficult. Picking up the tubes won't be too bad as long as the rover can drop them onto the ground.
Well, not to mention everything's going to have to survive 2 launches now, right?
Well, sure, right? Yeah. So I guess I could speak real quick about that. After we pick up the tubes off the ground, and we'll insert them into this cylinder called the Oz, and that Oz is the payload for, like Holly's talking about, a ascent vehicle, a Mars ascent vehicle. So it'll be the first time, lots of first time Mars sample return 2, the first time we're launching off of another planet, or Mars. We've launched off the moon, obviously. The first time we're launching off Mars and coming back to Earth. So they have to survive that launch. Like the tubes had to survive the launch from here, the landing on Mars. They'll need to survive the launch from Mars and the landing on Earth. Landings on Earth are more difficult on hardware than landing on Mars. So after we get those samples back to Earth, it's going to be come into the atmosphere, and we're going to crash land into Utah.
Excellent. All right. Next question. I think we have a little bit of feedback. Next question. How do you think Perseverance discoveries will revolutionize space exploration? That's a big question. I don't know if we have time to really go into that, but
how do I think Perseverance is going to revolutionize space exploration? Well, I talked about some key parts, like experiments like MOXIE. We're enabling an understanding to even go there, for humans to go there. So one major aspect that Perseverance is revolutionizing for space exploration is enabling crewed missions to Mars.
Yeah, absolutely. Right. Cliff, he wants to know, do you think SpaceX is going to leapfrog the sample return mission? Do we know what the sample return mission is scheduled?
It's either going to be 2026 or 2028.
Okay.
On that 2 year.
Yeah.
I don't know. Jeff's opinion. I don't think SpaceX is ready to send people to Mars yet. So now SpaceX may be ready by the time we get the samples back in time to look at them. So just because we launch in 2026, then it's 5 years to do the work. We're probably not looking at having samples back here until the early 2030s to actually look at from Mars. So from that perspective, maybe Cliff, I wouldn't call it leapfrogging. It's just the way things work.
Things take time.
Things take time.
That is actually time for us, speaking of which. Thank you so much, Jeff. That was awesome. That was an awesome presentation. If anyone has more questions for Jeff, you can reach him through people on the event site. You can also reach out. Do we have any other contact way of finding you?
No.
Nope.
I'll pay attention to the site.
Yeah. All right. Thank you so much, Jeff. That was great. I really appreciate your time today.
No problem, Holly. Happy to be here.
All right.
Thanks, everybody.
All right. Thank you.